Now in this video we're going to walk step by step through the 4-step process used in inference procedures and do an example using our bead sampling of a confidence interval for a population proportion. So our 4-step process, which I really want you to follow every time, this is going to help you out with organizing your thoughts and getting full credit on the AP exam, for example. You state the goal. What am I trying to do? I want to estimate the proportion of red beads in the container. What's my method for wanting to do that, and have the conditions been met? So I state my goal, then I check my plan. I want to make a 90% confidence interval for one proportion. So I have to look at the 3 conditions. My procedure, I've decided to use 50 beads here rather than 20 because turns out my 20 would not support the 3rd condition. So I'm going to randomly select 50 beads. So there's my random sample. I know that 50 is less than 10% of all the beads in the big container because I'm sampling without replacement. Now the 3rd condition can't be checked until I get a p-hat. So I'm going to take a sample. So I took a sample of 50. I got 10 out of 50 that were red, and that's a 0.2. So now I'm going to go back and check my condition. 50 times 0.2 is 10. 50 times 1 minus 0.2 is 40. Both of them are greater than 10. I forgot to state that. I need to state that. Both greater than or equal to 10. So that looks like a 50. So the normal model can be used. All right, now that I know that my conditions are met, I'm going to go look at here's my p-hat plus or minus my z critical value. Well, I want to do a 90% confidence interval, so I'm going to do inverse norm of 0.95 because that encompasses the middle 90% plus the 5% that's over here. And that's 1.645, so that goes here. And then I'm going to do my standard error of p-hat, which is 0.2 times 0.8 all over 50, p-hat, q-hat over n. And then if I multiply these 2 numbers together, I get a margin of error of 0.09231. So it's basically 0.2 plus or minus 0.0931, and that gives me this interval here. If I subtract the 0.0931 from 2, I get this number, the 0.1069, and then this is adding the margin of error to 0.2. 0.2 will always be the middle number of this interval, plus or minus, in this case, about 9.3%. Now my conclusion then, so that was my show the work part, formulas, calculations, sketches of models if appropriate. And you've been doing this actually with a normal model, but you've just been doing these last 2 parts, the show the work and write the conclusion part, but now we have to add the state my goal and check my plan. So write a conclusion. I am 90% confident that the interval from 10.69% to 29.31% contains the true population proportion of red beads in the container. So this is the template we learned before when we were talking in section 8.1 of how do we write about a confidence interval. Now there's one other thing that I want to do because I have kind of a wide range of values. I would like to be a little more precise in my estimate. So what statisticians do when they want to be more precise in their estimate is they pick a level of precision that they want and then decide what sample size they need to get that level of precision. So let's say that I want my margin of error to be plus or minus 5% or plus or minus 0.05. What size sample would I need? Because I know if I increase my sample size, it will decrease my margin of error. But what size sample do I need? So the way I set this up is I look at just the part that is margin of error. I know that margin of error is equal to, let's write that ME. Margin of error is equal to the z critical value times the standard error, p-hat, q-hat over n. So I fill in everything but n and then solve that for n. So my desired margin of error is 0.05. The z critical value that I need, move the wrong thing. The z critical value that I need for 90% is 1.645. So I put that in, 1.645. And then I have to put in a p-hat and a q-hat. Well, if I don't know anything about that population, what should p-hat and q-hat be? Well, the fact is I do know some things about that population. It turns out that when we did our class, all of our class intervals, we all took samples of size 50 and we made an interval. These are the intervals we got. So it looks like all but one of the intervals kind of cover this area here. So it looks like that my sample proportion, my population proportion is somewhere close to 0.3, maybe slightly less. But just for sake of argument, I'm going to say let's just assume p hat of 0.3 from my previous work. Okay. Now, if I had no previous work, what would I use for p hat? I would use p hat equals 0.5 if totally unknown. Now, why would I use p hat equals 5? Well, it turns out that 0.5 times 0.5 is the largest numerator I could get in this radical. And so then if I have the largest possible margin of error, then I know that my sample size will be sufficiently large for any value of p that I happen to get. But since I do already have a pretty good idea of what p hat is from my previous work, that's what I'm going to use. So I'm going to put 0.3 times 0.7 divided by n. Solve that for n, and I just recommend using the solver on your calculator, although you can solve it algebraically. But let's just, if we solve this for n, we end up with 227.3. Now it turns out that we want to always round up because 227 is just a little bit too small to guarantee my 5% margin of error. But 228 then should cover it. So always round up no matter what decimal place you have. So I'm going to use n equals 228 as my sample size. So now what we did as a class is we all took samples, well, half of us took samples of size 228. One person held the beads to make sure they didn't fall off the desk and spill all over the place, which did happen one year, and it took about 5 minutes to gather them. So the entire class took about 5 minutes to gather them. So we don't want that to happen again. So one person held onto the bead container, and the other person took 2 full paddles plus another 28 beads and counted how many red ones out of 228 there are and formed another interval. So our interval then would have looked like something like this. Whatever p hat they got, p hat plus or minus 1.645, and then this would have been the p hat, q hat, but then 228 here. So since this number is so much bigger than 50, then that's going to make my margin of error smaller. Well, after doing that, here are 3 class examples of what we got. One got 0.227 to 0.325. 22 to 32, that's a space of 10, so that's a margin of error on either side of the middle of 5%. 0.25 to 0.35, 0.22 to 0.32. They're almost identical with each other, and they're all plus or minus 5%. So this just confirms to me that the true population proportion is about 0.275, it looks like. It really does work to plan your n ahead of time. Now we're done with the topics in section 8.2, and you are ready to start some problems.